Good morning, everyone. So, today we are going to discuss two algorithms which are useful in two aspects, like they are useful in prediction as well as they are useful for solving the system of equations when you do the estimation. So, without wasting time, we will get into this. So, the first algorithm is Durbin-Levinson algorithm. Now, this algorithm is useful for forecasting, as I mentioned, forecasting as well as in estimation. So, if you remember that we have this equation while estimation as well as in forecasting, we need to obtain these coefficients from the autocovariances. I mean, so you have this is the matrix, the inverse of that matrix, and this is that vector. You remember these notations, so I'm not repeating them. This is there we introduced when these are when we started discussing the prediction, we introduced this, and you might have seen this also in the case of estimation. Now, once you have this equation, we have the forecast mean square error expression is given by this. Now, one of the problem that I mentioned at that point of time is as n become larger and larger, this matrix dimension get increases, and then you will have difficulty in solving this system of equations. So there is an algorithm which basically gives you this solution in a recursive manner by avoiding the inversion of such large matrix. So I'm not going to the proofs of this algorithm, and most of your software or most of the software uses this algorithm to solve. Now the algorithm is very simple. You can see that the phi n is given by this formula, gamma n minus summation j equal to 1 to n minus 1 phi n minus 1 j gamma n minus n minus j nu n minus 1 inverse. So this is for n equal to 1, 2, etc. And this is of course nn, and nk is given by this recursive relation. Nk for k equal to 1, 2, etc. n minus 1. So when these coefficients are different, it is given by this, and when they are same, it is given by this. And then this in this equation, you have this nu n fellow sitting there, and the nu n is given by this. Of which of course phi 1 is gamma 1 by gamma 0, and gamma 0 is nu 0 is actually gamma 0. Now in this expression, if you look carefully, phi and n are nothing but the partial autocorrelation function. Actually our intention is not to find we just want these coefficients which solve this, but in the process, if you actually get these coefficients, you can see that phi and n, the last one, which is basically the partial autocorrelation function, and the standard error of one-step forecast is given by square root of nu n, because this is the forecast mean square error, and the square root is the square root of nu n, where nu n equal to gamma 0 j equal to 1 to n 1 minus phi j square. Okay, so that is obtained from here actually. So this is what the Durbin-Levinson algorithm is. So let's look at with an example. So use the algorithm to start with phi 0 equal to 0, phi 0 0 equal to 0, and nu 0 of course gamma 0. And for n equal to 1, you get this equation, which is obtained from here, because you get n equal to 1, gamma 0 minus gamma 1, this is 1, all these are 1, or you can actually get it from here. Nu 1 is nu 0 into 1 minus phi 1 square, and that is this. And phi 1 is gamma 1 minus, this is for, this term will not be there, so this will be there. So you can see that gamma 1 minus 0, this term will not be there because this is not there for n equal to 1, because then this will become 0. You cannot run from 1 to 0. You can run from 1 to 1 or 1. So that's why n equal to 1 to 2, etc. Well, and then you have for n equal to 2, we get phi 2 2, which is given by this equation. Where did you get it from? Yeah, it is coming from this. You substitute for n equal to 2, and then that requires new one, which you already computed. So you have new one inverse, and new one you have already computed. So you get phi 2 2. Now, sometimes we may be interested, only this type of coefficient. We may not be interested in this, but the algorithm actually can be used to find both. So phi to 1, that means this is for this k is less than n, so we can compute all these quantities. And so you have here phi to 1 is phi 1 1 minus phi 2 2 into phi 1 1. Where did you obtain it? Because you obtain it here using this equation. So we can get this from here, which is phi 1 into 1 minus phi 2 2. And if you start writing this, you can see that this is nothing but gamma 2 minus phi 1 1 gamma 1 upon gamma 0 into 1 minus phi 1 1 square. Now you substitute for one of the phi 1 1, gamma 1 by gamma 0. So you can actually divide by gamma 0 throughout, which will leads to rows. So instead of, you divide by gamma 0 throughout this. So you'll get this equation. And once you have this, we can actually, V22 is available now. So we can get nu 2, which is nu 1 into 1 minus phi 2 2 square. Nu 2 is nu 1 into 1 minus phi 2 2 square. So that's what this is. So this is for n equal to 2. Now you can continue to do this, and then we can compute all the coefficients. Okay. So this is how the algorithm. See, what is this by this? Actually, I avoided, so I get all these coefficients. I avoided solving this. Now for n equal to 1 and 2, you can actually go and find the inverse of this matrix. But what happens that if n is quite large, this is really difficult. So this kind of an algorithm is going to help you. Now here is an exercise for you. You can compute for n equal to 3, phi 3 3, phi 3 2, phi 3 1 and nu 3 using that formula. And for AR2 model, obtain phi 1 1, phi 2 2 and gamma. Now, I have actually mentioned this without specifying what is this gamma 1, gamma 2, etc. Now, depending on the model, you get this expression for gamma 1, gamma 2, and accordingly, you can actually solve them. So that's what, so in the case of AR2 model, we obtain these quantities. So I've given you the hint. You can use the Yule-Walker equation and then obtain the expression for rho 1, rho 2 and rho 3. And once you have the rho 1, rho 2, rho 3, then compute phi 1 1, phi 2 2, phi 3 3. So in terms of, first you get rho 1, rho 2, rho 3 in terms of this, and then compute phi 1 1, phi 2 2, phi 3. How do you get it? You use this formula. Phi 3 3 is, use this formula. Phi 1 1, phi 2 2, phi 3 3. Okay, which you can obtain from this. And the relevant things are available here. Okay. So here the answers are given, so you can verify whether you are getting the correct answer or not. And what do you expect phi 3 3 in the case of AR2 model? Because phi 3 3 is the PSEF, and we know that beyond order 2, all the partial autocorrelation functions are going to be 0. So phi 3 3 has to be 0. That's why phi 3 3 is 0. So you can see, and the last coefficient is the order. So you can phi 2 2 is phi 2. You should get this. So it gives you a quick check whether what you are doing is really correct or not. Now let's look at the next algorithm. The next algorithm, so this algorithm are generally used for AR type of models, whereas if you have MA or ARMA type of models, we have another algorithm which also do more or less similar things. But the beauty of this algorithm, that earlier algorithm demands the process to be stationary, whereas here we don't have that condition. So the process need not be stationary. So you can talk about, gamma ST, okay, because otherwise we talk about gamma H. So now we can talk about gamma ST. So the coefficient, so this algorithm is stated in this way. Again, the same similar kind of a thing. Notations are slightly different here. because we have to talk in terms of KST. So you have this particular kind of a thing. So what is this theta n minus k? These are the coefficients which are obtained. Instead of phi, we denote it by theta. This has nothing to do with the ARMA kind of notation. These are basically solving those system of equations. Okay. Now which uses, because if you have a non-stationary matrix, non-stationary process, your matrix, it will be like, 1 2 1 3, these will be different. Whereas in the other cases, this 1 3 is nothing same as gamma 2 because of stationarity. So you don't have that in this context. So that's what, whether the stationary or not, irrespective of that, it is possible to find. What is the algorithm? The algorithm is theta n minus k is given by this equation, and recursive, again recursive, because these are smaller than this. So you compute them recursive manner and then get this, which uses the forecast mean square error also. So what is basically is like the coefficients are obtained using the forecast mean square error at every stage, and then updating it kind of, that's what is being done. So we solve nu naught first, and successively first you get nu naught, and then you get theta 1 1 nu 1, theta 2 2, theta 2 1 nu 2, etc. So I can show you this in an MA model. So if xt equal to zt plus theta zt minus 1, for this is basically the kappa ij in this notation. Kappa is basically stands for the covariance. So, and k11 is nu 0, which is the variance. So you can see that kappa ij is 0 for I minus j greater than 0. This is because a moving average process is 1 dependent. So beyond 1, this is going to be 0. So KII, whenever I is I, it is sigma, it is variance basically, sigma square into 1 plus theta square, and KII plus 1 is theta sigma square according to this notation. So we have this. So that leads to, you can see that, of course, this is a general thing. So now if I start getting those coefficients, this is general in the sense, this is only the covariance I have written. Now you have to apply this and then try to get this theta n minus k in this formula. So if you do that, first, as I told you, you have to get nu naught first. So nu naught is nothing but the variance, which is given by this. So nu naught is this. Then I will get theta n1, and theta n1, the formula is theta n1. So this will be, you have to subtract n minus 1 here, and that will give you nu n minus 1 inverse theta sigma square. This is not difficult. You can actually substitute and see. So I'm not spending much of time on that. You can just take this formula, substitute, and then you get it. You get it from here. Okay. This is actually the last coefficient because you are at n. This is n minus 1. All others are 0. So that's the beauty of that. So theta nj is 0 for 2 less than or equal to j less than equal to n. Theta nj, when this j is theta n1 is this, theta n2, theta n3, theta n4, all these are 0 for j equal to 2 to n. And we can get the expression for nu n. If you remember, nu n expression is this. So you substitute that and you will get, so actually you get the previous one square, which gives you a sigma. So this is, what is this? Kappa n plus 1, which is just variance, 1 plus theta square into sigma square, this one. And this one will give you theta square, sigma square, and one more sigma square will come because you are squaring that. Actually theta sigma square. So theta sigma to the power of 4 into nu n minus 1 inverse, which is obtained from here. So once you have that, so you have this. Where did you get this? Because this is here already we have computed that. So that is nu n minus 1 theta sigma square, and there is already a theta there. So that is what square is coming here. So you get this particular equation. So this leads to this is how you compute. This is a simple demonstration. Actually, we don't have to do much on this because manually we don't even use this for order of 1 or 2. Basically, it is useful for higher orders. Now there are certain general remarks that now there are a couple of more algorithms, but we are not discussing them. And anyway, I will not ask you to prove these algorithms. I will not ask. Maybe at the maximum, I will ask you to state them in an exam. But most of the software use them to solve. You know that we use this for solving the at both places like estimation as well as prediction. Let's do the innovation algorithm coefficient. Now, look at the Durbin-Levinson algorithm. It basically tells you the x1 is to xn in the representation of this kind of a representation, the prediction, theta n j xn plus 1 minus j. So, these coefficients are obtained using the Durbin-Levinson algorithm. So, this is what the Durbin-Levinson algorithm. Whereas, this theta nj, this is for phi nj, theta nj are obtained in the innovation algorithm. So this is basically a linear combination of the predictions. So you have theta n plus 1 minus j minus its best predictor, that's the innovations, and the sum of these innovations. So this is what innovation algorithm gives the coefficients of this in the expansion list. So the above expansion, now we say that what are the use of this? There are a number of advantages deriving the fact that the innovations are, these innovations are uncorrelated, and they also can be greatly simplified in the case of Varma PQ process. Now the innovation representation of xn plus 1 is, now if you simply take xn plus 1, we can write it as xn plus 1 minus this curl plus this, and that can be written, we can actually write this because this has a representation theta which we have written here. See this, each of them in this expansion, so that the same thing can be used here, xn plus 1 minus this quantity n equal to 0, 1, 2, etc. With theta n 0 is 1 is useful for computing one-step predictors recursively once these have been determined. So the innovation algorithm helps generates the mean square error, whereas the Durbin-Levinson algorithm is basically in terms of prediction in AR type of models. Yeah, I think that's all about it. Thank you.